In this video I am going to explain the need for quantum mechanics, that is why we need quantum mechanics. You can also view this video as a starting point of my lecture playlist of quantum mechanics. In this video I am going to explain that why classical mechanics is inadequate to explain some observational facts. So first of all I am going to introduce you the existence of atom. How classical mechanics, or you can say classical electrodynamics, is inadequate to explain the existence of atom. Obviously you have read about atom. Atom is consists of protons and electrons moving around it. So when electron, that is charged particle, moves around proton, it basically accelerates because it's circular path. So according to classical electrodynamics, it should radiate, and when it radiates it should lose energy, and when it lose energy it will fall on the proton, and the atom should not exist according to the classical electrodynamics. We have read about it. So you see clearly classical mechanics is inadequate to explain the existence of atoms. So total failure of classical mechanics or classical electrodynamics. Second example I will provide you, that photoelectric effect. You have obviously read about photoelectric effect. Is plus 2 syllabus, is in first plus 2 syllabus. Photoelectric effect, you can say that when sun rays falls on a metal and the electron just comes out of that metal, and I'm not going to detail of photoelectric effects. I'm just say that you cannot explain photoelectric effect through classical mechanics. You can never. As for now, you say that Einstein was the first one to introduce quantum. You cannot say quantum mechanics clearly. It was quantum theory that he used to explain the photoelectric effect. So photoelectric effect is one of the first example that we need quantum theory. Classical mechanics is clearly inadequate to explain. And in photoelectric effect, Einstein introduced the quanta of energy, and the quanta of energy was first discovered by Max Planck. So to explain the black body radiation, so black body radiation is also you can say this is the first observational fact. The black body radiation is the first observational fact which clearly says that classical mechanics is clearly inadequate. So black body radiation, photoelectric effect, and existence of atom. These are the examples. These are the observational facts that clearly goes against the classical mechanics. Now Compton effect is there also. Compton effect you have obviously studied in BSc, I hope. Compton effect is something like photoelectric effect, and you cannot use classical mechanics to explain Compton effect. If you use classical mechanics to explain Compton effect, you will see that only one kind of frequency you should get in Compton effect. But the observational fact is that we have more than one frequency in Compton effect. So classical mechanics is clearly inadequate to explain Compton effect. So quantum effect, photoelectric effect, and these kind of examples were coming in the 19th century, the end of 19th century and the first half of 20th century, that says that classical mechanics, the end of era of classical mechanics, you can say. Dual nature of particle is kind of a phase between quantum theory and quantum mechanics. When dual nature of particle was discovered theoretically by de Broglie, before that there was quantum theory, which consists of Einstein's postulates about the quantum of light, Bohr's postulates about the atomic structure, and quantum theory was also there. So quantum theory was before dual nature of particle, and then dual nature of particle came. And after that, I will explain later how quantum mechanics started. There is a slight difference between quantum theory and quantum mechanics. Now, what is dual nature of particle? I hope that you have studied dual nature of particle in quantum theory in BSc level. So, dual nature of particle is that a particle has a wave structure and also a particle structure. Now, how a particle can be both particle and wave? This is kind of a radical change between classical way of thinking and quantum way of thinking. So I'm going to explain first that how a wave can be treated as particle, and how a particle can be treated as a wave. Now first of all, I'm going to explain about the experiment. Now a particle nature of light. You have already studied that light is a wave, is electromagnetic wave. So, but here I am going to say the particle nature of light. Obviously, you have studied Fourier effect, Compton effect, and in those experiments, you cannot explain the phenomena by saying that light is a wave. So, when Einstein came with the idea that light is a particle, so what do you think that what light actually is? Light is particle according to Einstein in phenomena like Fourier effect and Compton effect. But phenomena like interference, phenomena like diffraction, you cannot explain those effects of optics by saying that light is a particle. So we need both ideas, that light is a particle and light is a waves. Okay, so here you can say that light is both. Light is particle and also wave. Now you can say that this is only constrained to the light, and this is not constrained to light. Every particle, everything you can say, everything is both particle and both a wave. Now let's take the case of electron. You have seen that in Bohr's postulates, electron is treated like a particle, and you also have many effects Wilder experiment. Those experiments said that electrons is a particle, but there is also interference of electrons. That is like if I have an electron band here and I emit electron, and where I have a screen, I will have interference pattern. That pattern is clearly like a wave nature. So if you say the electron is a particle, you can never explain why this interference pattern comes into the picture. If I say the electron is a particle, then the screen should have like this. The screen should have this pattern if electron is particle here. But what you see is that electron gives the pattern of this, and this pattern is only given by a wave. If there are, instead of electron, there are light, we'll have this one. Okay? So light is a wave and this is this one. But if electron is a particle, then this electron should not have given this interference pattern. The pattern should be like this. But instead of this, we have this pattern. So electron shows a wave nature. So electron which has a particle nature also shows a wave nature. So this idea that the particle, every particle has a wave nature and every wave has a particle nature. This is a dual nature of particle. Okay. So this introduces a radical change in thinking, and this I am going to say this is like phase change. Quantum theory to quantum mechanics. It is also said that de Broglie himself never understood what he actually postulated about the dual nature of particles. The effect of dual nature of particles is far than what de Broglie ever wondered.